Omkar, what is this deal with astronomy? Why are we uh, coming back to astronomy again and again? Even the message that you sent me, first 30 minutes are going to be astronomy, and then we'll study degrees and radians. What is this? What is this thing about astronomy?
So astronomy was the primary area of application of geometry in the ancient times. So if you look at uh, education, right, in those times, I'm talking about, say, classical Greek or Roman education. It was in the elementary school, they would study grammar, logic, and rhetoric, right? Grammar, because you have to know how to speak your language properly. Logic, because you were expected to argue your point of view using the language you learn. And rhetoric, not just logically argue, but persuasively argue in a way that moves your audience, because that was
Fascinating. Yeah.
important for you know, in a democracy, right? So these were the three basic subjects that you were taught. And then on top of it, there were four more subjects which were part of your secondary education, so more advanced education. And uh, one of them was geometry. Geometry was the primary way in which mathematics was done. There was no algebra at that time. And then geometry was applied to astronomy. So, so that was the thing. The other area of mathematics that was there was number theory. And number theory was applied to music. And that's a legacy of Pythagoras and his followers. So these four areas, geometry, number theory, astronomy, and music theory, these were the four advanced subjects. So the
Hmm.
three basic subjects, grammar, logic, rhetoric, plus these four advanced subjects, geometry, astronomy, and number theory, coupled to music, these seven were known as the liberal arts, the seven liberal arts, which every free citizen in the Roman world was expected to learn. So as we go through this, uh, as we go through more and more classes, it will become more and more clear why um astronomy provides an excellent context to learn a lot of things that are part of our syllabus, but which are presented without that context. And so we don't
Excellent.
understand where
So,
they come from.
Omkar, I also want to understand. I think we have 2, 3 minutes before we'll jump right in.
Mm.
So, when Newton came up with Newtonian laws, was he also trying to study some phenomena in astronomy and trying to make sense of it?
Yeah, astronomy was his primary focus because for him, you know, he wanted to explain the laws of nature, I mean, the laws of the universe using in a unified way. So before Newton, the laws that were applicable to the entities in the night sky, celestial physics, were those laws were completely different from the laws that applied to things on Earth, terrestrial physics. So Newton unified b- uh, terrestrial physics and celestial physics by showing that just one set of equations can explain things happening everywhere in the universe. You don't need a different set of laws in the celestial world and a different set of laws here.
Guys, you don't have to record this session. We are recording it. We will put it on YouTube channel. The link of the YouTube channel is on Telegram channel at various places. I'll put the link here also. So don't worry about anything. We will clean up the video. We will put it on YouTube. You just spend your time trying to understand things, trying to learn physics, and hopefully in the process start enjoying it. Right now, I keep using this phrase. It is karele ka juice. It should be watermelon juice. Okay, so Omkar, over to you. Let's start. Actually, one more minute. Guys, any specific thing you want to observe, you want to share with Omkar in this class? This is going to be a shorter class, around an hour. We are then going to meet. So today is about application of some maths, which is
Hello.
applicable from in physics. And on Sunday at 10 a.m., we are going to do the next theory class. That is going to be a longish 3-hour class. So that's what it is. I'm going to put all of you on
Am I
mute.
audible?
Uh, you're audible. Please don't ask whether you're audible or not. It is irrelevant whether you're audible or not. So I am putting everyone on mute. And Omkar, let's start. You will have to unmute yourself, and Omkar, you can start.
Okay. So, welcome back to our second session together. So, just to quickly recap what we did last time, in case you forgot the big picture. Last time, we looked at the broad questions of what is physics, why to study it, and how to study it in a deeper way, not just the superficial reasons that we might have had so far. And then we started on that journey by taking one big question as our launching point for exploration. And this big question was, what is our place in the overall map, or maps are 2D, so let's call it, what is our overall place in the 3D structure of the universe? So we as human beings have to come up with a model of the universe. And um, if we assume that all modern scientific knowledge is wiped out from our brains, obviously it was not there in ancient times. So if you put yourself back into a farming society, say in India or Greece at that time, and you had to rebuild all this knowledge from scratch, what would be, what would your own um, what would your own model of the universe be based on observations, evidence, experiments, and logical reasoning? And what we said is, towards the conclusion of last class, we said that a flat Earth cosmology, a flat Earth, some kind of flat Earth cosmology, would be a good start. It would explain um, a number of things that we see around us. So, um, the model that we had last time was a spherical universe with a flat Earth at the center. When viewed from the top, the flat Earth looks like this. It's a circular disk with the landmass of the Earth um, shown here in some crude way, but surrounded by a single ocean on all sides. And so that's what we are seeing. This is the side view of that, which is just a line, but from the top, it would seem like a circular disk. And there was an axis of rotation. So this spherical universe has a boundary, has an outer boundary in which there are stars, right? There are stars that are embedded in this outer boundary, uh, which we called as the celestial sphere of stars. And this entire sphere rotates around an axis. How did we come up with this model? Because when we look at the night sky, we see the stars rotating in circular trajectories around a single point in the northern sky. There is a star called Polaris, or the pole star, which is almost at the center there, but every star is seen to rotate around that point. And one way to explain it is to say that, well, we ourselves are rotating. Like if I see my fan um, rotating over my head, The simplest explanation is that it's the fan that's rotating, but it's also possible for me to shut off the fan and rotate, and start rotating my own body in the opposite direction, and I would still see the same phenomenon. But the possibility of the Earth moving in any way was ridiculous at that point, because any kind of motion of the Earth is something we should feel. Like when there's an earthquake, we feel it, right? Even a small earthquake, we feel. So um, any kind of major motion, like the entire circular disk revolving, would be something we should be able to feel if that was actually happening. So this idea was never entertained seriously because it would just seem ridiculous. So it's the stars that are rotating, and the best way to explain why they are rotating in synchrony is you put them all in the uh, embed them in the surface of a single starry sphere, the celestial sphere, and make that single celestial sphere rotate. And
Omkar, I
that
have a
is,
quick disturbing question.
yeah,
Is it because everything is rotating very slowly, that's why we don't feel it?
everything is rotating. You mean you're talking about the Earth?
I'm talking about the Earth.
Uh, well, yeah, I mean, once you get to Newtonian physics, you would see that the Earth is almost an inertial frame, not exactly an inertial frame of reference, but almost. So the acceleration, so acceleration is what we can detect. Um, like when you are
Like,
accelerating in a car.
I mean, if you
Mhm.
see Ayush's message, he's saying,
Oh,
I think we can't imagine rotating Earth due to gravity and relative speed. So, uh, these are very interesting observation. I don't think this observation is right.
due to gravity and so firstly, what is gravity? In those days, the word gravity just comes from the Greek word gravitas, which means heavy, right? So the ancients would also say that, yeah, things fall down because of gravity. Well, that's just another way of saying things that are heavy fall down, right? So space, if you recall last time, was thought of as having an absolute direction. This direction is up, this direction is down. And so things with gravitas, things that are heavy, fall down. That would be the ancient notion of gravity. So let's not bring in modern ideas into this model. Um, my point was just that having, trying to explain the motions of the stars by having the Earth itself rotate in the opposite direction would contradict the physics, right? You don't see anything in this world if you just keep if you look at daily objects around you, they don't start spinning in circles forever, right? Even if you make them spin, they come to a stop. So it would be ridiculous to imagine the whole land on which you are living rotating around for no reason. Does that make sense? So, and plus you should be able to feel it, right? Because even if you're
Oh God, sorry, I muted you as well. Sorry. I'm sorry. I muted you.
what was the last thing you heard me say?
Uh, I'm a bad student. Someone should tell, but everyone is muted.
Yeah. So, yeah, what I was saying was, did you hear me talk about gravitas, like things that have things that are heavy?
Gravitas we did after that. After that.
Oh, okay, okay. So, yeah, so it would seem ridiculous for the ancients to think of the Earth moving in any way in our model of the cosmos, because when we are traveling in a bullock cart, we feel the motion, and if we are going faster, we feel the wind on our face, right? If you're going in a car, of course, there were no cars that time, but if you're going in a chariot that's going really fast, you would feel the wind on your face. And so there's no reason to think that the entire landmass on which we are living is moving in any way. Uh, Daily objects around us don't move in circles forever, right? Even if you get a ball to start spinning, it comes to a halt. So even the physics of that, from the point of view of the physics of that time, having the entire landmass of the Earth rotate for no good reason uh, forever, it would just seem very ridiculous, right? So this is a natural way to think of the universe. You can have things move forever in circles in the night sky because that's where the gods live, those are divine entities. So circular motion might be natural there in the night sky. In fact, it is natural there as we see from our daily observations, but it's not natural on the Earth. What's natural on the Earth is that things fall down when we drop them in a straight line. Okay, uh, so that's the model we had, and we also saw that there were practical um, uh, observations which pointed to the fact that the Earth is flat. Like if you plant yourself on a grassland or a surface, if you're sailing in the ocean, you would see the surface of the Earth going out, extending out in a flat way indefinitely, even though there are mountains and valleys. We saw last time that, they're more or less like blips on the surface, like creases on the surface of a towel. Um, so it's a pretty reasonable model to start out with. And I also mentioned last time that um, the fact that there is this fixed pole around which all the stars are rotating allows us to define absolute, absolute directions, um, not just for space, right? No, I'm not just talking about the fact that space has an absolute direction like up and down, but even on the plane of the Earth, as you're observing the pole star and as you see the constellations, the different stars, which I said maintain the same spacing relative to each other, and so you see the entire constellations move, preserving their shape. Um, this star, Polaris, or this center, which is called the North Celestial Pole, if you remember from last time, if you imagine dropping an object vertically from there, it would hit the horizon somewhere, and the direction in which uh, that spot would lie is called true north for you. And you can do this irrespective of where you are on the surface of the earth. You can identify which is the true north direction. And this north-south line, right, if you turn around, you would be facing south. And so this north-south line is called the meridian line. The meridian line. I'm saying local meridian because, if you're in a different place on the earth, that line would be different. And then if you stretch your hands out um, in the, facing north, then your hands would be along the east-west line, which we will just call as the latitude line. Okay, so that's how you can identify the four directions, north, south, east, and west, by looking at the stars. Okay, so um, the other thing I mentioned last time was that there are other entities in the night sky which don't which actually move relative to the stars. So they seem to wander, unlike all the stars here, which seem to rotate in synchrony. There are seven other objects in the night sky, which also rise in the east and set in the west, um, like the stars do. But of course, not all stars. As you see, there are a bunch of stars that don't rise and set at all. Those are called circumpolar stars. But in general, the stars rise in the east, set in the west. And there are these other seven um objects which we called as the wanderers, right? The Greek word for that is planetes, so we call them as planets. And we saw that there were seven of them, which seem to change their relative position uh, to the stars. So today you might see them in front of some constellation. Um, a few days from now, you may find them, in front of some other constellation. And so these were the sun, the moon, sounds very strange, right? That we think of the sun and the moon as planets. In fact, it would be ridiculous to call the Earth as a planet in that time, because the Earth is stationary, right? The sun and the moon are the wanderers. And then you had Mercury, you had Venus, you had Mars, you had Jupiter, and then you had Saturn. Uranus and Neptune were not visible through the naked eyes, and so we had to wait till the invention of the telescope for them to be discovered. But we have seven planets, and so I told you last time how the notion of a week comes about from the fact that these seven planets, viewed as seven gods, were worshipped in Babylonian times, and there was a day set aside for the worship of each of them individually, and that's the origin of our 7-day week. Now, what we want to do today is we want to um actually go back to this picture and focus on these circular paths that are followed by the stars around the pole star. Okay, so I just want to review one basic property of all circles. And this might seem obvious, but all circles are similar to each other. They all have the same shape, right? If you look at triangles, rectangles, they don't have the same shape. Well, squares do, regular polygons do. Regular polygons of different sizes, you can say, have the same shape, but not rectangles and triangles and so on. So, what does it mean to be similar? Having exactly the same shape, even if the size is different, is what similarity is about. So, if I take two circles of different sizes, same shape, different sizes, I can imagine taking the first circle, magnifying it by some factor. Maybe I magnify it 2 times to make it 2 times bigger, and I get the other circle. So whenever we magnify something, what happens is that all the lengths that are drawn on that smaller figure are going to get magnified by that factor. So if I magnified this circle 2x, that means any length that I could have drawn on this circle. For example, if I drew the radius would double. If I drew the diameter would double. If I measured the circumference would have doubled, right? So in fact, so if C1 was my circumference for the smaller circle, that would get magnified to C2 by whatever the magnification factor is, 2 or whatever. The diameter of the smaller circle would have also gotten magnified by the same amount, right? By the same amount. So I can claim that C2 divided by C1, the magnification factor for all lengths, is the same. So the magnification factor for the circumference is the same as the magnification factor for the diameter. Right? C2 by C1 is the same as D2 by D1. And so I can say that C2 divided by D2 is the same as C1 divided by D1. Right? So the ratio of the circumference to the diameter is the same, remains the same when we magnify something. Right? And in fact, that's true of any shape. If you take a right angle triangle, you magnify it, you'll see that the ratio of any two lengths on that triangle will remain the same even after magnification. And that's why we give those ratios some names, like we call one ratio as sine, another ratio as cosine, another as tan, and so on, tangent. Uh, anyway, trigonometry is separate. I'm not talking about that here. We are just talking about circles, and my point here is that the ratio of um, circumference to diameter is the same for all circles, because starting from one circle, I can generate any other circle by just choosing the appropriate magnification factor, right? In some cases, I might shrink the circle to make it into the other circle. So this ratio is called pi. Okay, so the Greek word, so in the English language we have the letter P, right? In Sanskrit we say pa. Uh, for Greeks that letter was called pi, and so perimeter is what you would call something that goes around a shape, right? So uh, for a circle, the perimeter is called circumference, but the letter pi gets used uh, to remind us that it's the perimeter. So P, right? So when you see when an ancient Greek saw the word pi, actually they didn't use the symbol pi at that time, but um, this reminds us of the letter P today. Okay, which is why it was chosen as a symbol, not in ancient times, later, but that's the reason. So anyway, so the circumference by the diameter is pi for every circle. Now we know that the diameter itself is double the radius, right? So we can write c by twice of the radius is pi. And so we can say that this property is true for every circle, that the circumference of the circle is a constant multiple of its radius, and that constant is 2 pi. So we're going to keep this in mind as we go back to this picture and notice the fact that when a star or any object goes around a circle, from the standpoint of the center, if you imagine placing yourself at the center, you would see that object turning, right? So let's say your eyes are constantly fixed on that object. You would have to turn to track that object as it goes around the circle. And so we need a measure for the amount of turn, right? The amount by which you would need to rotate your gaze as, for example, this star goes from here to there, right? So initially you're looking in this direction. When the star is here, the direction in which you're looking is there. So you would have rotated your gaze from here to there. And so by how much did you turn? That is what the angle measure is. Right? That's what the angle measure is. So if I have a circle, um, and let's say I'm tracking an object which was initially here, and after some time it is seen to be there. So I'm looking in that direction. The amount by which I turned, right? I'm calling that as, let's say, theta. So theta represents the amount of turn. And the question is, what is a good way to measure it? What is a good way to quantify it? Okay, so let's go back to our flat Earth cosmology, and um, let's say this is our universe, this is our flat Earth, and I'm looking at the side view, but let's say you are located here, you are situated somewhere in the center. Uh, the sun, the sun is rising somewhere in the eastern direction. Let's say this is the east-west line. The north-south line is actually a line that's going into the plane of the blackboard. So imagine that the north direction is going in, the south direction is the direction that's coming out. Okay, so you are looking north. So you are facing north, much like in this figure. Okay, it's just that somebody is observing you from behind. So they see you standing on a flat plane like this. So how does the sun move, uh, or any star move, right? It rises from the east, and to you it appears as if it's going in a counterclockwise or anti-clockwise direction, and then it sets in the west. Okay, at least according to some cultures, it would go down below the plane of the earth like that, and then it would emerge out again the next day from the east. So if we try to map this to a coordinate system, right, I'm sure you must have studied about the Cartesian coordinate system, where we imagine taking this infinite plane of the blackboard here and putting two perpendicular number lines, right? And here I'm putting you at the origin, the intersection of those two perpendicular number lines, so that any point in this plane gets a unique x address and a y address, right? But anyway, we're not concerned about the x and y addresses here. We are concerned about the trajectory of the sun as it goes around the earth. So firstly, the normal direction of motion is counterclockwise. Okay, so that means whenever we develop a magnitude for the amount of turn, our convention is going to be that angles that are counterclockwise are going to be positive. So if I see something going in the clockwise direction, and if I have to quantify its turn, I would give it a negative number. Okay, so that's one convention we can start with, that anti-clockwise turns are positive angles, clockwise turns are going to correspond to negative values of angles. Okay. The other thing I can see from this diagram is that the sun first, when it rises, um, it is in one of the four quadrants. So if you imagine dividing this plane into four quadrants, the sun first enters this top right quadrant. So I'm going to call that as quadrant 1. The next quadrant it enters is quadrant 2. The next quadrant it enters is quadrant 3. And the next quadrant it enters is quadrant 4. So the convention is going to be that whenever we talk about quadrants, we are going in this anti-clockwise direction and following the order in which the sun enters those four quadrants. Um, when the sun is at the highest point in the sky here, if you imagine putting a vertical stick in the ground, because the sun is at the highest point in the sky, you can imagine that the shadow of that stick is going to be the smallest at that point. So that point of time during the day is called noon. Noon is the time when the shadow of a stick on the ground is the shortest, and it is the point of time when the sun is directly over the meridian line. Okay, the meridian line is something that's coming out or going in, depending on how you look at it, in the north-south direction. So when the sun is directly over the meridian line, that's noon time. So before noon, it's in quadrant 1. After noon, right, that's where the word afternoon comes from. Afternoon, it's in quadrant 2. And then in the night, it's in quadrant 3 and quadrant 4. And you can imagine this for all the stars as well, including the moon and the planets, which also rise and set, similar to the sun. All right, so that's our broad framework so far. Now, we are living in an agricultural society, okay? So that means we are living in settled homes. We have a fixed horizon. Every day and night when we look around, the horizon does not change. And that allows us to come up with new ideas, to see patterns which may not have been evident to hunter-gatherers who were constantly moving around and who did not have a fixed horizon. So one of the things we can see, if we were to, for example, uh, rise just before sunrise, okay, and look out at the eastern horizon. So I'm just going to label this as the eastern horizon. I'm looking east. The sun rises somewhere in the east. But just before the sun rises, it would be dark. And so I would be seeing stars rising. Okay, the stars also rise from the east. They also set in the west, right? So the ancient Egyptians saw that just before some sunrise, sometime in, maybe currently the month of July, there was a very bright star called Sirius. Sirius is actually the brightest star in the night sky. They would see Sirius rising above the horizon, and then the sun would rise almost at the same time. And when the sun rises, it blocks out the view of all the stars, right? Then we don't see any stars because the light from the sun is so bright. So they noticed that there was a day when Sirius appeared just above the horizon, and then it would vanish because the sun would rise almost at the same time. Now, the next day, if you get up next day before sunrise and you keep an eye out again on the eastern horizon, you would see Sirius rise, but you would notice that it goes further up in the sky before the sun rises. And again, once the sun rises, its view disappears. Then the next day, you get up and look at the eastern horizon. You see this bright star Sirius rise, and you see that it goes even further up in the sky before vanishing uh, with sunrise. Okay, so what's your conclusion? Your conclusion is that the stars that make up the celestial sphere are actually rising every day a little faster, a little earlier than the sun. Okay, and this makes sense because that is why the sun is a planet, because right on day one, the sun is right next to Sirius. And then on day two, Sirius is a little ahead of the sun. And on day three, it's further ahead, right? Um, and so it keeps going further and further ahead. And so the sun is kind of lagging behind Sirius. Okay. Now, if let's say you are running on a circular track, let's say there is a circular track on which you're running, and um, there is a faster runner than you, right? There is a runner who's faster than you. There's an observer who's looking at you as you go round and round along this circular track. And there is another runner who's also running around the same circular track, but that person is faster than you. So an observer at the center of the circle will see that the gap between the faster runner and you is going to keep increasing. But and if you run long enough, then that faster runner is going to actually catch up with you from behind if you give it enough time. Right? It will appear as if you are ahead of that runner, but actually the runner is almost one full circle ahead of you. So in the same way, when Sirius keeps going further and further and further up, and when I say up, I mean it's actually going around a circle, right? We're talking about a 3D sphere around which it's going. So it's following a circular track, and the sun is following its own circular track, but it's going slower, right, along that track. Um, Sirius is going faster, and so there comes a point when Sirius catches up with the sun from behind, and after and that happens. The Egyptians noticed that this happens after 1 year, right? So after 1 year, Sirius will come back to its original position, and you will find it rise just before the sunrise, um, as you saw a year ago. And this is what you see with all the stars. Now, for the Egyptians, this was an important event because this also coincided with the flooding of the Nile. So, just like in India, you have monsoons. Um, in East Africa, there would be monsoons in the highlands and mountains of Ethiopia. And then the rain that fell there would actually flow down, just like, the rains cause rivers to start swelling, the Ganga, Yamuna, and all that. In East Africa, um, there is this Nile River, which gets uh, flooded because of these rains in July or so. And the Egyptians were living further north, right, in the desert. They didn't know anything about, you know, the monsoons and the highlands and all. What they would see is the level of water in the Nile would rise sometime in July, and then it would flood their land. And they would be waiting every year for it because when it floods, it would deposit fertile uh, soil on the banks, and so they could use that fertile soil to grow their crops. And so, actually, if you just go 1 mile away from the Nile, in those days, it would all be desert. Right? So all the Egyptian cities were along the Nile. So this was an important event for them. It was important for the survival of their society to track when would the Nile be flooding. So that was the beginning of the year. And it's obviously, you don't expect the Nile to flood on the same day every year. So they wanted something more reliable to predict, you know, uh, before the flooding of the Nile, how do you mark the beginning of a year? You need something to happen uh, regularly every year and reliably every year on the same day. And this is what that event is. So this is called the heliacal rising of Sirius. You don't need to know this term, but the heliacal rising of Sirius was an event that the Egyptians tracked, and it marked the beginning of the year for them because that's when they thought the Nile is soon going to flood. So, all right. So, what do we make of this? If you count the number of days from one heliacal rising to the next, the Egyptians and the Babylonians counted and they saw that the number was close to 360. It was 365. Uh, and 365 is not a very convenient number. And so, um, by the way, how is it 365? So it turns out that Sirius rises uh, earlier by 4 minutes every day, right? So every day it gets a 4 minute lead. It gets 4 minute extra time in the sky before the sun obliterates it. So the question is, how many such 4 minute intervals, after how many such 4 minute intervals, or after how many days would Sirius come back to the same point? Right? So it gets a 4 minute lead every day. So after 15 days, it would get 4 times 15, 60 minutes lead, right? 1 hour lead after 15 days. And if there are 24 hours in a day, then, multiply 15 by 24 and you would get 360, right? So obviously this is not exactly 4 minutes. It's a few seconds, um, plus or minus 4 minutes. So the exact number would be 365, although even 365 is not an exact number, but around 365. But for the Babylonians and many other ancient people, they wanted the number to be something easy to work with. And so they defined the length of a year to be 360. They chose to define the length of a year by 360. And then every few years, they would add maybe an extra month in the year to sort of bring the error back down close to zero. Okay, so uh, 1 year, so 1 year was defined to be 360 days. So like I said, 4 minutes times 15 would be 1 hour, and times 24 would be 24 hours, right? So when you do 4 minutes times 15 times 24, that's 24 hours. And so this number is 360. So after 360 days, you would get back Sirius at the same location relative to the sun. So 360 is what they decided to work with. Now 360 is a very good number because it has a large number of factors. So when you use 360 in your calculations, um, you're likely to get numbers that are easier to work with. All right. So that means now if we imagine the sun um, in the with the celestial sphere in the backdrop, what's happening is the sun is lagging behind by a certain amount every year, and after 360 days, it's back to the same location in front of the celestial sphere, right? So if you imagine labeling the point directly behind the sun on the celestial sphere with a dot. Every day you would have to put a new dot. And after 1 year, if you connect all the dots, you would get a circle on that 3D celestial sphere, right? That circle marks the path of the sun relative to that celestial sphere. Does that make sense? Because like I said, the sun and Sirius are both going along a circular track. The sun is just going a little slower. And so if you just look at the stars or the constellations that are directly behind the sun, those would keep changing during the course of the year. Those would keep changing during the course of the year. That is how agricultural societies survived, because they could look at which constellations were behind the sun. Well, you can't see the constellations behind the sun, but you can predict them, or you could look at the constellations on the opposite side, right, at midnight. Um, which constellations are high up in the sky at night? Um, um, and based on that, they would know where the sun is relative to the celestial sphere. And based on that, they would know how the seasons are changing. And it was important to figure out the right uh, day to plant the crops so that you could have enough food in your society for the survival of your society, right? As the seasons change. So the constellations behind the sun would keep changing. And so the sun would actually follow the point behind the sun on the celestial sphere. If you track that, that would change, and the sun would follow a trajectory in front of the celestial sphere that would be a circle on the celestial sphere. Does that make sense? I hope that if anything feels unclear, Kapil, you can feel free to interrupt me. Um, I can explain in more detail. So,
Sir, we are enjoying the session a lot.
sure, thank you. So, because it takes 360 days to make a complete circle, it takes 360 days for the sun to make this complete circle around the celestial sphere. In 1 day, the sun must be turning relative to the center of that celestial sphere by an amount that is 1/360th of a full circle, right? So the amount by which it turned in 1 day is what we call as 1 degree. And that became the unit of angle, which you have been probably using till class 10th in mathematics. So a full circle is divided into 360 degrees. And this degree sign, as you see, is itself a circle, right? Indicating that it's representing um, the amount of turn on a circle, and 360 makes a complete turn. 1 degree would be 1/360th of that. It is the amount by which the sun moves or lags behind actually on the celestial sphere, or it is the amount by which the stars go ahead of the sun every day. So, uh, this is actually not a natural unit if you think about it, because we use the decimal system nowadays for everything, right? If you think about mass, once you define what 1 kilogram means, and if you had to divide it into smaller pieces, we choose 10 or some power of 10, right? For example, 1000, we divide a kilogram into 1000 pieces and we call each piece a gram. Or we divide a meter into 100 pieces, we call it a centimeter. Or we divide a meter into 1000 pieces and we call it a millimeter. So we always cut something into smaller parts uh, by using this number 10, because we have 10 fingers on our hand. And so because counting in its most primitive form was done using fingers, and so whenever you hit a count of 10, that would be like, one complete uh, hand has been counted, and then you would start counting the numbers beyond that by reusing the same fingers. Uh, So 10, the decimal system, emerged out of the fact that we have 10 fingers on our hand. So it makes sense then to divide even a full turn into 10 pieces, or maybe 100 pieces, or 1,000 pieces, depending on which angles what the size of that unit is for common calculations that you encounter. But it should have been some power of 10, but it's not. Okay. And this is an oddity. If you think about it, this is an oddity. It's not something that we normally do for physical quantities. By the way, one additional note, astronomical note about this. You remember last time I told you that a month, so the moon also goes through um, all of its phases in a time that was known as 1 month. So actually, if you do the same thing for the moon, you will find that the moon lags behind by an even bigger amount, not by 4 minutes, but almost 50 minutes every day. So in 1 month, the moon would be back to roughly the same location relative to the stars. Now, the sun and the moon were the biggest objects the ancients saw in the night sky. And so they naturally wanted that there be a whole number of months making up a year. See, we have two different cycles now. There is a cycle from the sun, there is a cycle from the moon. And you naturally want you naturally want to interconvert between them, right? How many months make up a year? Well, you would see how many full cycles of the moon make up a year. And unfortunately, that number is not a clean whole number, but it was somewhere roughly close to 12. And so the ancients divided a year into 12 months for that reason. Now over 1 month, the sun would move by, so it's moving by 1 degree every day. So if we divide a year into 12 months, 360 divided by 12 is what? 30 days, roughly making up a month. So the sun would have to move, if it moves by 1 degree every day, roughly, 30 degrees every month. So a 30-degree rotation or lagging behind relative to the celestial sphere would change the constellation the sun is in. Right? That's a significantly long time interval that the entire constellation would change. On a day-to-day basis, the sun might move a little bit, inside a constellation, but over a month it would be pretty much in a different constellation. In fact, what the ancients did is they took the path that the sun takes around the celestial sphere and they cut it up into 12 constellations corresponding to each month. Those 12 constellations were called the constellations of the zodiac. So they were special constellations. The entire celestial sphere has lots of constellations. You look in all directions, there'll be some constellation or the other that the ancients came up with. But focusing specifically on that circular path on that celestial sphere that the sun goes in front of across the entire year, the constellations that appear behind the sun during the course of a year, those 12 constellations were called the constellations of the zodiac. And those correspond to our star sign, right? So if you look at the month in which you were born, um, on the day of your birth, if you look at the constellation that's directly behind the sun, of course, you can't see the constellations that are directly behind the sun, but you can see the constellation that's directly opposite to that uh, in the night, right? So by looking at what the opposite constellation is, you can figure out what the constellation the sun is in front of, and that becomes your star sign. Um, that's just a side note, okay? So since it's natural, therefore, or the ancients thought it was natural to divide a year into 12 intervals called months, because 12 phases of the moon, 12 full cycles of the phases of the moon make up a year. When it was time to divide a day into a certain number of parts, like to track the time, they chose 12 intervals again. Okay, so a day the time between sunrise and sunset. The day is the time between sunrise and sunset. That was divided into uh, 12 parts, and those we call as hours. The same thing was done for the night. The time between sunset and sunrise also divided into 12 hours. So the total time, the time between one sunrise and the next sunrise, would be composed of 24 hours. Okay, so for a long time, it was sufficient to just measure time in terms of hours. You didn't have to subdivide it further. But when people became more conscious about how they're spending their time and they wanted to track time at a more granular level, they decided to divide an hour also into a certain number of pieces. And unfortunately, once again, um, because this was done by the ancient Babylonians, it was not done according to the decimal system, because the Babylonians used a base 60 system. The Babylonians used a base 60 number system. So they divided time into 60 parts. If they subdivided time into 60 parts. So an hour got divided into 60 minutes. And then if you have to subdivide a minute further, that would be into 60 seconds. In fact, 1 degree, an angle of 1 degree is also subdivided into 60 minutes. We call that as minutes, right? Even though it's not time. It's a a subdivision of angle, but an angle is divided into 60 minutes, and a single minute gets divided into 60 seconds. Now this is done because of the base 60 system. So if we have an angle like 40 degrees and 20 minutes, right? This is equivalent to an angle of 40 plus 20 minutes means 20 by 60 degrees. Okay, so 40 1/3, or you can say 121 by 3 degrees if we were to express it as a fraction. So this is the only um, um, area in physics or physical quantities where we don't use a base 10, a decimal number system. But um, we could now think of how to invent a more natural unit for measuring angles than this artificial degree system. In fact, we could even go beyond that and ask, is there a more natural unit for angle that does not even rely on the decimal number system, that doesn't even rely on the fact that we have 10 fingers on our hands, which is also kind of like an accident. If we had 12 fingers on our hands, then we would not be using a decimal system. So is there a natural unit? Is there a natural unit that even aliens or some civilization, if it exists outside of the Earth, might also resonate with? Right? Is there a natural unit for measuring angles? So to think about this, let's consider a circle of radius 1. Let's consider a circle of radius 1. We call this a unit circle. There is a natural property that we do know about, which circles satisfy, which is that the circumference divided by the diameter is pi. Okay, this is natural. It doesn't depend on what number system we use. So this means that my diameter, which in this context is 2 units, is equal to pi. So the circumference of a unit circle would be 2 pi units, right? So that's one thing we know. So this means that if I were to walk around a circle by 2 pi units, I would be making a full turn, right? So the amount by which we rotate our vision is proportional to the arc length that we walk along this circle, right? The amount by which we rotate our vision, the amount by which we rotate our vision to track an object is proportional to the arc length. That is clear. So why not define the amount of turn as the arc length? Why not define the angle measure as that arc length? The bigger the arc length, the bigger the angle, right? So what does that mean? That means a full turn is equivalent to an angle of 2 pi, because a full turn is an arc length of 2 pi. So why not just use the same number for the angle measure and say, well, the angle measure is also 2 pi. A half turn would be an arc length of pi. So we can say, well, let's call it an angle of pi.
Omkar, this is pretty cool. I think let the students absorb this because I am also getting a feel of radian now. This
Okay.
is very good. Guys, are you able to understand at this point? I think it dealing with length of an arc sometimes can come across as slightly uncomfortable because arc is not a straight line, right? So we find it difficult to visualize that. Can we define angle measure as the arc length? If you are able to understand it, very cool. You can absorb it for 15 seconds, then we can move forward. Veer and Advik, are you here?
Yes, okay.
Yeah, I'm just seeing a question here. What is Rashi? Yeah, Rashi refers in Indian astrology. The Rashi would be the zodiac constellations, right? It's actually not the oldest. So if you go back to further behinds, right? So these zodiac constellations were, as far as my understanding goes, imported from outside because um, the Indian astronomy used to be based on the moons, the constellations behind the moon rather than the sun, and so they had 28 or so nakshatras, they called it, which were either individual stars or groups of stars, which represented, each day, because one month is roughly 28, 29 days long. And so if you look at the star that's directly behind the moon, or a group of stars directly behind the moon, then across a month you would have 28 of them, 28 or 29 of them. So those were the nakshatras. And then the rashis were based on the sun, right? What's behind the sun? Uh, not every day, but every month, if you look at what's behind it. One
Excuse
issue
me,
is that these constellations are not of the same size, right? It would be nice to have had the night sky divided perfectly into, constellations that span 30 degrees. But some constellations are smaller, others are bigger, and there are actually empty regions in the, along that spherical path that the sun follows, sorry, circular path that the sun follows on the celestial sphere. So people had to create constellations there, even though there were there were no bright stars in some of those regions, like Cancer. Look at the constellation Cancer the crab. There are no bright stars in that. You can hardly see it, can hardly make out. But to create 12, right, because of this astronomical need, um, people created constellations so that we would have 12 of them, or 12 rashis, as we say.
sir, I want
Um,
to ask a question, please.
um, Kapil, do we take questions at the end, or should I take them right now? Because I still have a little bit of material to cover.
We should take them at the end.
Okay.
Let us finish it up and
Yeah.
then take questions.
Yeah,
Is it
let's
okay?
finish the
Can we
material
wait
and
for the
then
questions till the end?
yeah. Okay. So a quarter turn corresponds to an angle. So a quarter turn corresponds to 1/4 of 2 pi, right? 2 pi is the entire circumference. And so a quarter turn would be 1/4 of 2 pi. So that would be an arc length of pi by 2. And so let's call it an angle of pi by 2. Right. Now, this is assuming that our circle is 1 unit in radius. Right. We are talking about a unit circle. So we are defining our angle measure as the arc length along a unit circle. Um, um, so um, now you may ask, well, what if the circle was a general circle of radius r? Can we extend this to any circle of radius r? Now, obviously, the arc lengths are going to change. So, arc length depends on the radius because a full turn around a circle of radius r would be of length 2 pi r. Right? So, it depends on the radius. So, how do we define an angle measure if we had to use a circle of radius r instead of a circle of radius 1? So, let's say I draw a circle of radius 1 here. Sorry, it's not an exact circle, but uh, so let's say this was a concentric circle. This radius is 1 and the whole radius is r. So uh, let's pretend that we walked from here to there, and so we turned by this angle, right? Whatever that angle measure is. So for a unit circle, we would look at what this arc length is, this red arc length, and call that as our angle measure. So what about a circle of radius r? So a full turn, right? A full turn, which would be an arc length of 2 pi r, is something that we still want to map to an angle of 2 pi. So we still want a full turn to be an angle of 2 pi, which is what we got from the unit circle. But a full turn has length, has arc length 2 pi r. So for this larger circle, what we want is the arc length of 2 pi r should map to an angle of 2 pi. Right? We want an arc length of 2 pi r to map to the same angle 2 pi for consistency. So what do? Well, we just take the arc length and we divide it by r. We just remove the r. How do we remove the r? We just divide by r. And so we can come up with a rule that if the arc length is s, so just divide by r to get the angle measure. So if the arc length is s, right, we will say the angle measure would be the angle measure representing the turn from the beginning of, from where we start and where we end, representing the turn, would just be take the arc length and you divide by r. Right? And so that is what we call our angle measure, or new angle measure, or more natural angle measure. It's, if you want to interpret it, it's like how many radii make up that arc length, right? That is our angle measure. We know that for a unit circle of a full turn would be made up by 2 pi radii, because 2 pi times 1 makes up the full turn. So if you were to, actually, let me show you an animation from Wikipedia. I think there's a nice animation of what a radian is. Kapil, just let me know if you see the portion of screen. Hold on.
Yes, we can. The screen is gone now.
Yeah, I'm just trying to. Okay, Google Chrome. Do you see the Wikipedia page here now?
Yes, we do see it.
Okay, so here's a unit circle diagram, and let's wait for it to. Let me actually refresh it because. Okay, so here we have a circle that is being drawn of radius r, and so if we want to define one radian, we could take one radius and just imagine an arc length of one radius. That angle would be 1 radian. Okay, so if we have an arc length that's double or triple that, we would get 3 radians. A little more than that would make up pi radians. Obviously, we want 2 pi of 2 pi radians to make up a full circle. And so if this was a unit circle, we would say, if we had a 1 unit radius, we would just imagine an arc of length 1, right? And define that as uh, as our new unit of angle, which is what we are calling as a radian. So the reason it's called a radian is we are asking how many copies of the radius make up that arc length, right, corresponding to that turn. How many copies of the radius should we lay down back to back so that we get that arc length? Let me go back to the uh, blackboard here. So when we define our angle measure like this, another way to say it is our arc length is our angle measure times the our angle measure theta times the radius r. So that means how many copies our angle is telling us how many copies of the radius to lay down back to back so that we get that arc length. So either way, I mean, whatever way you want to make sense of this, the point is that we started from a unit circle and we said a natural unit of angle is just the arc length because the bigger the arc length, the more the turn. And so we defined the arc length for a unit circle to be our angle measure, and so to handle the case where we are dealing with circles that are of radius r, we just scale things down, right? Another way to think of this is just scale things down to a unit circle, whatever the arc length is, that would be our angle, because that's what we decided. So how do we scale things down? How do we bring this circle down to a radius of 1? Well, we just divide everything by r. So whatever arc length we had in this bigger circle, if you divide that by r, that becomes our new arc length on a unit circle. And that by definition is our angle. So theta is s by r. That's another alternate way to visualize this if you're a little confused by this new angle measure, which is called radian. It's called the radian because it is derived from the fact that, I mean, the name is derived from the fact that if you look at this equation, or actually even if you look at a unit circle, how big is an angle of 1 radian? We know that an angle of 2 pi radians would be the entire turn, right? A full turn. So an angle of 1 radian would just be, take this 1 unit radius and imagine an arc length of 1 of the same length as the radius. And this angle that we get would be 1 unit, right? Because we know that 2 pi units are supposed to make up a full turn. And so a 1 unit arc length would make up an angle of 1. And when you magnify this by a factor of r, you get this. So an arc length of r would subtend an angle of 1 radian at the center. Okay, so that's where things come from. I mean, this new unit comes from. So an arc length of 1 radius is equivalent to an angle of 1 radian. And this definition does not depend on the civilization, right? Whatever be the number system in the civilization, the point is, whatever the length of the radius is, we could do, what the Wikipedia animation showed, which is just imagine an arc length of that same, which is the same length as the radius, and whatever angle it subtends, that's 1 unit. And this is natural because we know 2 pi, the entire circumference is of length 2 pi r. So we want a full turn, therefore, to be 2 pi radians. So our starting point, we don't define what, if you're a little confused by this, don't think of this as the starting point. Our starting point is this. We know that the angle by which we rotate our vision is proportional to the arc length. So why not define the arc length itself as the angle measure? And to make it do this in a way that's independent of radius, we imagine a unit circle. Do this for a unit circle. And then for any other size circle, just scale things down to a unit circle, and that would give you the angle measure. So if you first start with this and then ask, what does it mean for the angle measure to be 1? It means the arc length has to be 1 in a unit circle, right? That's where we get this from. For a circle of radius r, what does it mean for the angle to be 1? Well, for a circle of radius r, scale everything in this diagram by a factor of r. So it means the arc length has to be r. So we would get a diagram for a general circle like this. This length is r, and then the angle would be defined as 1. And instead of a circle, we write a small c to denote radians, right? 1 with a small c, and again the c represents the letter for a circle. It's like in degrees, you actually draw a little circle. For radians, you just write the symbol c. So the last part for today is how do we interconvert from degrees to radians? So convert, let's go in one direction first. Convert degrees to radians. By the way, there is a big advantage of using radians in calculus. I cannot explain it right now to you, but once you understand what derivatives and integrals are, the formula for derivatives, particularly involving trigonometric functions, are much easier when your angles are in radians. Whereas if your angles are in degrees, those formulas would be more complicated. So that's the reason why we always stick to radians in calculus, and because physics uses a lot of calculus. In physics everywhere, or at least in many places, not everywhere, but in many places, particularly places where you have to use calculus, you would always rely on radians. All right, so how do we convert an angle? Well, actually, let's start with the easiest example. 360 degrees, we know, is a full turn, and our radian unit is such that a full turn is how many radians? It's 2 pi radians. Does that make sense? That 360 degrees, which is a full turn, in the would map to what in radians? Well, if we go back here, the amount by which we rotate our vision in a full turn would be the arc length, right? So that's 2 pi. for a unit circle, and so 2 pi radians. So once you have this, then everything else follows. So 180 degrees would be pi radians, divide everything by 2. Obviously, 0 degrees would also map to 0 radians. How about 90 degrees? If I want to convert 90 degrees into radians, what would that be? Actually, before that, 1 degree. 1 degree would be how many radians? Well, if I use this and I just divide both sides by 360, 1 degree would be 2 pi divided by 360, or pi by 180 radians. So now I get a formula for converting any angle in degrees into radians, because if 1 degree is pi by 180 radians, then 90 degrees would be pi by 180 times 90, which is pi by 2 radians. And many times we don't even write this little c. We just say an angle of pi by 2. It's understood that we are referring to angle in radians unless we explicitly write a degree symbol. Okay, so 90 degrees is pi by 2. How about other common angles which you will encounter in radians? 30 degrees. 30 degrees would be pi by 180 times 30. That's pi by 6. And I'm not going to write the c now because many times, you're going to see angles without any symbols whenever they are in radians. So keep in mind this fact. Right? Either 2 pi radians is 360, or you can say pi radians is 180 degrees. Remember one of these two. Either 2 pi is 360 or pi radians is 180, and you would be able to get the conversion for any other amount. So 60 degrees. So if pi radians, so here's how I could mentally do it. Well, pi radian is 180 degrees. So 60 degrees would be 1/3 of that, right? So 180 degrees is pi radian, 60 degrees is 1/3 of 180. So it should be pi by 3. But if I want to do it mathematically, I would do pi by 180 times 60, and I would get pi by 3. 45 degrees, 45 is 1/4 of 180, right? So since 180 is pi, 45 degrees would be pi by 4. Okay, so in general, we can say in general, when we have theta degrees, this is going to be equivalent. So to convert from degree to radian, you just multiply by pi by 180 radian. Okay, so pi by 180, by the way, in decimals is around, I believe, 0.017 or something. Okay, you don't have to remember that. Pi by 180 is the fraction that you should remember. So 1 degree is a very small quantity when you look at radians. So theta degrees would be just pi by 180 times theta. Right? Pi by 180 times theta radians. So now we can go the other direction also, if this is clear, how to convert from degrees to radians. Then we can go the other way, convert. So let's say we want to convert from radians to degrees. Again, our starting point can be the fact that pi radian is equivalent to 180 degrees, or 2 pi radian is equivalent to 360, whichever of these you want to start with. If I divide by pi, both sides, I get 1 radian. 1 radian is equivalent to 180 by pi degrees. Right, that's around 57.3. So in other words, if you have an angle of around 57.3 degrees in a circle, you're guaranteed that the arc length you're looking at is equal to the radius in length. Okay, so what would be, let's say, now if I want to convert, let's say, pi by 2 radians into degrees. If 1 radian is 180 by pi, I know the multiplication factor is now going to be 180 by pi when I'm converting from radians to degrees. Since 1 radian is 180 by pi, pi by 2 radians would be 180 by pi times pi by 2. That's 90 degrees. Let's take an angle we haven't seen before, say 2 pi by 3 radians. I'll give you 30 seconds to do this. 2 pi by 3 radians is equivalent to what in degrees? $120, yeah. So 2 pi by 3 times 180 by pi. So pi cancels out. 3 times 60 is 180. And so you get an answer of 120 degrees. So once you have this fluency in your mind that pi radians is 180, you know that 2 pi by 3 is going to be 2/3 of 180. So you can get 120 mentally in that way. So in diagrams also, you should be able to understand diagrams where the angles are labeled in radians instead of degrees. So I could have, let's say, an angle of 60 degrees written. But I should also be able to understand if the same diagram was drawn where the angle is shown to be, let's say, written as pi by 3. And likewise, as I said, when we measure angles, the reference point is the positive x-axis, because as we saw earlier, that's the direction in which the sun is rising. So imagine sunrise, the direction of sunrise is along the positive x-axis. That's our starting point. And counterclockwise is positive. So if this is 60 degrees, this angle would be called as minus 60 degrees, because starting from the positive x-axis, you have to rotate by 60 degrees in the clockwise direction to get here, right? We have to go down here in the clockwise direction. So this is minus 60 degrees, or equivalently, we would call this as minus pi by 3. How about a slightly more harder problem? Convert 40 degrees, 20 minutes into radians. Take a full minute if you want to do this. Okay, so let's see, 40 degrees, 20 minutes. Let's first, we actually did already convert it to degrees. So just in terms of degrees, this would be plus 20 by 60, right? 40 plus 1/3. That's 121 by 3 degrees. We did this earlier. So to convert from degrees to radians, we know that one radian is much bigger than 1 degree. So if you forget whether the conversion factor is pi by 180 or 180 by pi, you know that 1 degree is a very small amount, 1 radian is a big amount. So when you go from degrees to radians, you're actually going to reduce your magnitude by a big factor. So it's going to be pi by 180, not 180 by pi. Radians to degrees, you would be, because 1 radian is much bigger than 1 degree. So when you go from radians to degrees, you have to multiply by a big factor. So that factor would be 180 by pi. So here it's going to be this times pi by 180, which is 121 pi by 540 radians. Okay, I can just leave it like that. It's understood that it's in radians. So because radians, the formula for the measure of the angle is from arc length given to be the arc length divided by the radius, and so it's the ratio. The angle is the ratio in this formula. An angle in radians has no dimensions. For those of you who've done dimensional analysis, this is the ratio of two lengths. So, in terms of dimensions, a radian has no dimension, but it's still a unit. It's still a unit of angle measure, although it cannot be seen as defined in terms of any of those dimensions like mass, length, and time, and all which are common in mechanics. The other thing to be careful about here is when you're using calculators, whether handheld graphing calculators or online calculators, make sure that your calculator is in the right mode, the radian mode, when you are solving problems in physics that require radians. Okay, so by default, they may be in degree mode, or maybe by default, they are in radian mode. You have to make sure before you use a calculator that you choose the right mode, degree or radian, before putting in your numbers. Otherwise, you would get some nonsensical answer. Okay, I think Kapil, this is the theory and the few problems that I wanted to cover. We can take questions now.
So, guys, one thing which I want to understand from all of you, you must be wondering in your classes, this probably would have been covered in terms of a quick definition of a radian, a quick mechanism to convert between degree and radians. So I want to know, why should we spend so much time going through something which you technically learned in 10 minutes in class? Would anyone want to answer my question?
So may I?
Yes, please, Jia, please tell me.
Yes, sir. So because sir, now we are preparing for competition. So yeah, it's okay to learn it technically, but when we are going to learn in a longer way, so to retain this information, we have to go through this. Like sir is the PhD of physics, so that's why he knew all of this, and we are now in a competition level. So it's maybe about the place that we are now.
Okay.
Yeah, I
Double Z.
will just correct one thing. I'm not a PhD in physics. I'm a PhD in computer science. So physics is actually not what my degree is in. Um,
Sorry, sir,
so
my bad.
I'm not a physicist, but at the same time, I've gone through the system. I have learned physics at the college level, and I have spent time working on physics education for a few years. Yeah.
Double Z, you were saying to increase our curiosity. How did your curiosity increase in this case? You were curious, you would get up every morning thinking about radian, or that curiosity has been taken care of, or what curiosity are you talking about?
Can I answer this question, sir?
Okay, go ahead.
Sir, first of all, in these classes, we are understanding the origin of physics. So, from the starting, if we select any topic, we study about how the topic came in the mind of these ancient scientists.
Hmm.
Uh,
Yeah.
and and that the same thing which develop curiosity in our mind also. Like we are living the ages of that older scientists, and we are thinking the way as same as the ancient scientists think in the previous years.
Yeah. So Ayush, I'll tell you one thing. I think I want to share it with everyone. I'm beginning to understand the method which OD is following. Uh, as of now, we were given a laundry list of things. This is G, this is F, this is A, this is V, this is U. Circular motion को ऐसे handle करो, projectile motion go like this. We arrived at our current knowledge, which is captured in the books through the efforts of our forefathers. Last time we were at Aristotle, or we are still going to be on Aristotle on Sunday. We will slowly figure out at some point of time the model will get stuck, and then mankind being mankind, they being curious, they being trying to solve problems, what else someone should do while being awake. So people kept working on the problem till the time they started getting solutions that worked. So at least I am beginning to get a sense of, as we try and understand, someone in the beginning was saying, is this a history lesson? Yes, it is a history lesson. And through history, we are trying to learn how people have understood the nature around them. So, Omkar, that way, would we also learn how to solve problems? That is what students are, must be wondering. That okay, we are understanding, but are we also going to be able to solve inclined plane problems? And are we also going to be able to solve collision problems? And are we also going to be able to solve moment of inertia problems? By the way, moment of inertia in our development of the universe would have come fairly later, right?
Yeah, Newton didn't develop the concepts of rotational motion that you find in 11th class physics. That was developed after Newton.
Wow. Somewhere around, I think Kepler, at least in that chapter, Kepler is a scientist which has been mentioned.
Yeah, but Kepler was before Newton. Um,
Yeah.
yeah, rotational mechanics was developed after that because you need vectors. Newton didn't work with vectors. Uh, so as vectors were developed, then you had these and as rigid body motion was analyzed because Newton's focus was mostly on planetary motion and of
Right.
course things on the earth uh, insofar as they connect to the physics of the universe. But rotational motion and all for engineering applications, that wasn't his focus. So it was developed later.
No, it's fascinating, Omkar. I am beginning to get a sense that astronomy and the history of this knowledge, how it has developed and come to where it is, it would start kind of making sense rather than हमें बस ऐसा लगता है फॉर्मूला याद करो, क्वेश्चन में लगाओ एंड डन. नहीं, वैसा नहीं है. जब तक till the time we approach things that way, it would always be a drag. Otherwise, every question can be understood and can be treated just as a puzzle, as a problem to solve, rather than almost feeling as if it's a burden. So I think at least it's beginning to make sense for me. I don't know what students have to say, guys. Let's have a um, quick feedback from
Yeah.
you.
Yeah, I'll also add, Kapil, like for
Yeah.
example, this problem, I took it from the NCERT book. Um,
Okay.
but I think it was the math book rather than the physics book. But we did come to these problems, right? These are simple problems converting radians to degrees and vice versa. So naturally, we would be able to solve this, but with an understanding of what a radian actually means rather than as a formula. So memorization of formulas gets replaced by conceptual understanding, but you still have to go forward from there and solve problems to develop that fluency. So it doesn't negate what uh, coaching institutes are doing, but it's more like an add-on
Yeah,
prerequisite for which actually can make things a lot more interesting for you rather than burdensome.
correct. And I think the pace at which we plan to go, Wednesday class of some kind of problem solving, and Sunday a longish class in terms of diving into the theory, understanding how the body of knowledge has developed and built up. I think that is fantastic. So, guys, this is pretty much it for today. By tomorrow around 12 noon, we are going to upload this video. We won't do much of modifications in this. In the beginning, when I was talking, some of that chit chat that would be gone, and we'll provide the video right when Omkar dives into it. And this is pretty much it. We will meet on Sunday at 10 a.m. You have to design your schedule around the fact that we will meet every Sunday at 10 a.m. for 2 to 3 hours. So design your life around that. If you can't, you can always see the recording later. But it's always fun when these kind of classes are happening to attend them live. We will also consider whether we can do it live on YouTube. So we will let you know whether we continue on Zoom. What can happen is while this is happening on Zoom, the same thing is being live streamed on YouTube so that more people can participate, and YouTube can also push it to people who want to see similar stuff. We about us, YouTube knows better than we do. So that's pretty much it. Omkar, anything from your end? I think this is fantastic. Again, thank you very much. You're giving a lot of time for these students. I hope this will make the learning enjoyable to them, and they will start making sense of physics. And once they start making sense of physics, they would have found a fantastic companion in their life.
Sure, thanks. So do we have questions right now, or what? How should we just end?
Sir, sir, can we conduct the class on Saturday, because most of us who are going into coaching would have an examination on Sunday.
Jaidev, we are going to try and figure out. Most probably, it would not be possible on Saturday.
Okay.
So you can go through the recording. Omkar and I had a detailed discussion about it. So probably it would not be possible, but Omkar and I would have a quick chat and we'll see. But most probably it would not be possible. Okay, I think that's pretty much it. Any questions you have for Omkar? Otherwise, we will call it a day now, and we will say good night to each other, and we'll say good morning to Omkar.
Sir, being a dropper, can I watch these videos? Is these videos are beneficial for me, sir?
Kumar, this is a conclusion you will have to come to. These videos at this point of time are definitely not replacing uh, your requirement for coaching. So you will have to figure out whether these videos are helping you understand physics better. If you think it is not, and time is too short, don't attend them. But if you think they are helping you, then definitely attend them. I think it is a good supplement, a good vitamin uh, to what you are learning in coaching, because what you're learning in coaching might become dry in the way it is being taught. नेचर ऐसा है कि वहाँ पे उस तरह से पढ़ाया जाना जरूरी है, एंड वी आर वेरी कंफर्टेबल कि यहाँ पे ओमकार डज नॉट हैव टू टीच लाइक दैट.
Thank you, sir.
Excuse me, sir.
जी आयुष बोलो.
Sir, I want to ask a question from Omkar, sir.
हम्म.
Okay.
Sir,
Yes.
first of all, thank you for these wonderful classes. And secondly, I want to ask a question that in our Indian society, there is a belief that the people predict the future from the uh, zodiac sign. So I want to ask that what is the significance of zodiac sign in astrology or in predicting the future, as you told about zodiac sign in this class?
So there was a pervasive belief, not just in Indian society, everywhere around the world, that the planets, right, the seven planets, um, which um, move in the sky, which are seen to be brighter than the stars, often larger than the stars, that they have an outsized influence on our lives. And that's actually very obvious for the sun, because the sun is what causes the seasons. The sun affects our day and night cycle. And, our life, human life, I mean, all life on Earth depends on the sun, right? So it's kind of self-evident for the sun. But it was not an illogical step for the ancients to believe that the same thing is true for the other six planets as well, especially given the identification of the things we see in the night sky with uh, divinity of some kind, right? Either some kind of god or uh, at least divine in some way. So if if the sun can govern our life in such a close way, then maybe the moon also does, maybe the other planets also do. And so, um, how do you explain, the events that happen in your life, both, the good things and the bad things? Is there any way in which we can predict or control those events? So I think that was a key motivation for astronomy in that time. So astronomy and astrology were actually one and the same thing for um, even till the time of Kepler. I mean, Kepler and Galileo. Kepler was doing a lot of astrology. Like for him, his analysis of uh, the planetary orbits and all was governed by his unshakable belief in, there being a meaningful numerical order to things in the universe. And so uh, it was almost mystical. His physics was almost mystical, although today we just take out whatever his three laws of planetary motion as equations and we just look at it that way. But, over time, as modern science developed, uh, uh, scientists today would ask this question, what is the evidence that other planets or things other than the sun do control our life, and especially at an individual level, right? Like the time at which I was born, the constellations or the planetary configurations in the sky around that time. Does it really have an influence on my life? Now we can ask that question and not just answer it based on anecdotal evidence. Like if something happened in my case, I might attribute it, I would seek a cause for, why it happened to me and not to others. And then what's unique about me, right? One of the things that might be unique about me is the planetary configurations at the time of my birth. And so maybe that has something to do with, what happened to me. So, but today, we would have to answer that question about whether astrology has a scientific basis by looking at this question using a large data set, right? A data set that is not um, based on just anecdotal evidence, but based on uh, research on a large number of people, right? You take a large number of people, you look at astrological predictions for them, and then you see whether those predictions, you use statistics. Again, you have to use mathematics there, but it's like, similar to the kind of statistics that biologists would do to figure out the efficacy of a medicine. So, is it true that the astrological predictions are better than random guesses? right? And I have not gone deep into that question, but from whatever I see in mainstream science, scientists say that there is actually no statistically significant evidence for uh, uh, astrology being able to predict future events in your life on a large scale. It could happen that for individuals something is predicted and it becomes true. And then obviously, whenever individual events like that happen, then those individuals will swear by the truth of astrology. But when predictions don't happen the way they were supposed to happen, then nobody talks about it, right? So the things that get talked about are more the things that did happen. And we always know that, when you do large scale predictions, some of them are going to end up being true even by pure chance. So for that reason, I remain skeptical of astrology, but you know, uh, I I feel like if the evidence is there, then hopefully somebody will present it so that open-minded scientists could change their minds about this. But as of now, if you look at mainstream science, astronomy and astrology are like now totally separate. Um, but having said that, astrology did play a significant role in the development of science. So uh, naturally, that was a key motivator for many of the astronomers who were uh, trying to make better and better predictions for where the planets would be in the sky at any point of time, because it was super important to be able to predict where the planets will be so that you could plan to perform some rituals or some important function uh, at an auspicious time. And that motivated a lot of work in astronomy. So that's what I'll say. But personally, uh, I'm not convinced that, and at least in my case, even anecdotal evidence, when you look at what astrologers that my family has interacted with, what they said would happen and what did happen, there was not much
And
correlation.
obviously, guys, you can't ask what were some of those events. You're not going to get an answer. So, okay, should we end it here, guys? Any other question
Sir, a quick
or
question.
Kshitij, go ahead.
So, will we guys who attended the session today would be getting the link for the Sunday's class also? Or like we guys are being replaced by new students?
You are not being replaced, don't worry.
Okay, fine.
All right. Okay, Omkar, thank you very much.